I would like to take a little time to go over what's going on in the list of standard reduction potentials that you'll find in Appendix M in the back of your text. This also relates to Chapter 20, PowerPoint Slide 13 and 17. So what I've done here on this particular sheet is I've lifted just a select few of these reduction potentials that are listed in Appendix M. And each standard reduction potential that's listed here as a number, it's going to be associated with a particular half reaction. Now each half reaction is going to be listed as a reduction. So the cell potentials listed, let's just write it here, E0 in units of volts. Each cell potential is going to be listed as a reduction. So negative 2.38 volts, that is going to be the potential that one would get from the half reaction of magnesium gaining 2 electrons going to magnesium solid. Because we know that E0 positive is spontaneous, then we know that this reaction here is going to be pretty tough to get to go. It's not easy to do this. That's a very negative cell potential. So this is probably not going to happen. On the other hand, if we go down here, if we look at oxygen gas reacting in an acidic environment, getting 4 electrons and going to water, that's going to be quite easy to happen based on the positive cell potential for this process. Now, what you have to recognize is that for any redox reaction, you're going to have to link together, they sometimes use the word couple, but you're going to have to link together 2 of these half reactions. Because every time a reduction's going on, right, if this reduction is happening, there's got to be an oxidation happening somewhere else. So anytime I look at a redox reaction, I can go to this chart, and I should be able to find 2 half reactions, one in the forward direction and one in the reverse direction, that when I add them together, it'll give me the overall reaction for the redox reaction, and then I can calculate the cell potential for what's going on. Now I know you've already seen this, but I want to do this for this particular reaction that we've already run. We'll say that we're going to have copper 2 ion. That's going to react with the zinc solid. This is dissolved copper, by the way. And we're going to end up getting solid copper, and we're going to get dissolved zinc. Now, if I look through this list here, I'll see, well, I see a copper 2. So this reaction here is probably going to be something that I'm going to use here. And I also see some zinc as well. And if I look, I see that the dissolved copper 2, that's on the reactant side. And if I see the dissolved zinc in the reduction potentials, that's on the reactant side as well. So because these match, but this is on the opposite side, I'm going to leave this equation as written, and I'm going to flip this one. So watch what we do here. I'm going to write my reduction half reaction, and that's going to be copper 2 plus dissolved plus 2 electrons goes to copper solid. That's this one here. I write its corresponding cell potential. And then I write this one. I've got to flip one of them, right? There's got to be an oxidation somewhere, and this is going to be the oxidation. So I'm going to flip this. This is going to be zinc solid goes to zinc 2 plus 2 electrons. And because I flipped the reaction, I flipped the sign. And then when I add these 2 together, this number of electrons has to balance this number of electrons, and I get copper 2 plus solid zinc goes to solid copper and zinc 2 plus, and my cell potential is a positive 1.10 volts. And you should be able to do this for any particular reaction. Let's just try another one here. Let's try this process for a slightly more difficult reaction, this one here. 2 lead sulfate plus water going to solid lead, sulfuric acid, and oxygen. So I'm going to look at my table here. Well, let me slide this down so we can see the overall reaction. And look at this here. I see this particular reaction boy, that's got some lead sulfate on the reactant side. It's got some solid lead on the product side and some sulfuric acid. I think I'm going to need to use this equation here as my reduction. This, the lead sulfate's on the reactant side, and that matches here. So this is probably the reduction that's happening. And as I look at this, let's see. It looks like I'm going to need 2 of these, isn't that? Isn't that right? Yep. So I'm going to multiply this whole equation by 2. So let me write this down as my reduction. Let's see, I'm going to write 2 lead sulfate. That's 2 of this. I need to multiply this by 2, plus 4H plus 4 electrons. That's going to go to 2 lead plus 2 sulfuric acid. And this is gonna blow your mind. I'm gonna write this as negative 0.36 volts. Well, why didn't I multiply this by 2? You're probably thinking. And that's a really good question. We're going to take an aside here, and I'm going to answer that question. The unit of volts. Volts is a joule per coulomb. Energy per charge. Okay? And charge, the amount of charge that's delivered, that's going to relate to the number of electrons that get transferred. Okay? So we went from 2 electrons transferred here, and when I multiplied this whole equation by 2, we went to 4 electrons. But we need to pay close attention to the units. How much energy do I get per electron? It doesn't matter if I multiply this by 2. I'm still going to get the same energy per electron no matter what this is multiplied by. It's like asking, it's very similar to asking how many pennies per dollar. How many pennies per dollar? Well, if I have $100, there's still 100 pennies per dollar. If I have $1, it's still the case that I have 100 pennies per dollar. The volt is like that, okay? The volt is how much energy we're getting per charge, and that value is not going to matter by what, how many electrons get transferred. Just like how many pennies per dollar doesn't depend on how many dollars you have. It's always 100. The same is true for volts associated with a particular half reaction. The joules per coulomb is going to be the same regardless of whether you multiply this by anything or not. That's a really important point that you're going to have to remember. Okay, I know that's a long aside, but it's an important one. Now, here's our overall reaction. I want you to look through this list and see if you can't figure out which of these is probably going to be the oxidation half reaction. If I look, let me see. I've got some oxygen, and in this list, the only thing that's oxygen is this right here. And I've got some water as well. Hey, look, that's over here. So why don't and it's 2 waters, 1 oxygen, 1 oxygen, but I need to flip this. So why don't I just write this reaction down flipped? So it's going to be 2 waters going to O2, 4H plus, and 4 electrons. So let's write that down. 2H2O is going to go to O2 plus 4 electrons plus 4H plus, and the cell potential for that, I flipped it. I got to make that a negative 1.23 volts. So I'm going to write that down. We'll do it right here, negative 1.23 volts. Okay? Now I'm going to add these 2 half reactions together and watch what happens. All of this is on the product side. All of this is on the reactant side, and I got to make sure that my electrons are balanced, and hey, look at that, they are. So I can cancel the 4 electrons produced with the 4 electrons that went in. So there's a transfer of 4 electrons that goes on in this reaction. It looks like 4 protons go in, but hey, 4 protons go out, and look at what happens. We gain the net overall equation. 2 lead sulfate, check, that's this. 2 waters on the reactant side, check, gives me 2 leads, there it is, 2 sulfuric acids, and an oxygen. Look at that. It completely balanced. So these 2 half reactions, describe this overall reaction. And now, to find the cell potential for the overall reaction, we just add these two things together. So what's that going to be? A negative 1.59 volts. So it's about minus 1.6 volts. So as written, this reaction would probably not have, well, it's not going to be spontaneous. But in this direction, it would be. So if I flip it, let's see, if I have 2 lead solid, add a little sulfuric acid, you're going to need 2 of those, and some oxygen gas. That is spontaneously going to react to form lead sulfate and 2 waters, and I know that because I flipped this sign. The cell potential for this is going to be a positive 1.59 volts.